Thank you for introducing me. Hello, everyone. Let me introduce myself. I'm Mya Hlaing from the Natural Language Processing Lab, University of Computer Study, Yangon, Myanmar. Today, I would like to present about Generative Adversarial Network-based neural vocoder for Myanmar end-to-end speech synthesis. These are the outlines of my presentation. As all you know, text-to-speech model focus on synthesizing intelligible, natural sounding speech given the input text. And in recent years, end-to-end neural TTS model have emerged to simplify traditional speech synthesis pipeline, and their synthesized speech can be comparable with human recordings. End-to-end TTS model typically composed of two main processing model, spectral representation generator, and vocoder. Can you hear? Can you hear me? Yes. Spectral representation generator generate the spectral representation such as mel-spectrogram given the input test of phoning, and vocoder convert the speech waveform from the generated mel-spectrogram. And separately trained neural vocoder based on GAN generated adversarial networks have demonstrated remarkable capability in generating natural sounding synthesis speech. So in this word, we trained two GAN-based neural vocoder, parallel WaveGAN and HiFi-GAN, and we use this model in Myanmar end-to-end speech synthesis. And then we expand the ability of our trained vocoder in three texts: through mel-spectrogram inversion, generalization of unseen speaker, and Myanmar end-to-end speech synthesis. And to the best of our knowledge, this is the first effort to explore the advance of neural vocoder in Myanmar end-to-end speech synthesis. And the usable audio sample can be available online. And this figure shows the proposed Myanmar end-to-end speech synthesis. And we trained Taco-Tron-2 model and two GAN-based vocoder model, parallel WaveGAN and HiFi-GAN, and on Myanmar speech dataset, small dataset. And we combined these and train end-to-end and Taco-Tron-2 and GAN-based vocoder. We give the phoning sequence to the Taco-Tron-2. Taco-Tron-2 model generate the mel-spectrogram, and the generated mel-spectrogram are input to the vocoder, and the vocoder converts the generated mel-spectrogram to the speech waveform. Actually, Taco-Tron-2 use character sequence as the input. However, we trained the Taco-Tron-2 model on the phoning sequence because we want to alleviate the mispronunciation problem of phoning sequence in a small data set. And let me introduce about parallel WaveGAN and HiFi-GAN. Parallel WaveGAN is a distillation-free, fast and small footprint waveform generation method using GAN. The model is non-autoregressive at both training and inferencing. The generator is trained by jointly optimizing the multi-resolution short-time Fourier transform auxiliary logs and the waveform domain adversarial logs. And the discriminator is trained to correctly classify the generated sample as fake and simultaneously ground truth sample as real. Sorry. HiFi-GAN has been composed of one generator and two discriminator containing multi-scale discriminator and multi-period discriminator. The generator HiFi-GAN is a fully convolutional neural network with multi-receptive field fusion MRF module that can process the various length of patterns in parallel. In the discriminator bed, each self-discriminator of MPD handle equally spaced sample of input audio, and MST was used to capture constituted pattern and long-term dependency. And this is the data set we use in our training. We use Myanmar phonetically balanced speech corpus that is built from the basis travel expression corpus. It includes 4,000 utterance recorded by a native female speaker, and sampling rate is 16 kilohertz. In our training, we use 3,800 utterance for training and each 100 utterance for validation and testing. And I would like to present about experimental setup of parallel WaveGAN. We use 18-band Lord mel-spectrogram with band limited frequency range 80 to 7,600 Hz as the input auxiliary features, and with normalization was applied to all convolutional layer of both generator and discriminator. And the model was trained for 200 key steps, and the discriminator was fixed for the first 100 key step, and then both the generator and the discriminator were trained together. We used the open source implementation from this link. And for HiFi-GAN, we use the same configuration of HiFi-GAN V1 from the original paper, and we applied to train the model on Myanmar speech dataset. I mentioned in the previous slide, and 80-band Lord mel-spectrogram with band limited frequency range 80 to 7,600 Hz as the input condition. The model was trained for only 20 key steps, which is the same step used for training the parallel WaveGAN model. This is the very small step compared to the training step used in the original paper. They use 2.5 million steps. Each Vocoder model was trained on a NVIDIA Tensor KX0 GPU. And this is the experimental setup of Tacotron 2. We trained the Tacotron 2 model on the same Myanmar training dataset with 125 key stack with atom optimizer and a batch size of 32. In the training process, the guided attention loss was used to promote a fast and robust attention learning. We used ESP-net and end-to-end speech processing toolkits for modeling. This model was trained on two NVIDIA Tensor KX0 GPU. And for evaluation, we conducted 3 mean opinion score tests for ground truth, mel-spectrogram inversion, generalization to NC speaker, and end-to-end Myanmar speech synthesis. 10 needed non-expert speakers participated in all MOS tests, and subjects were given the synthesized speech or true model and ground truth audio, and they have to rate the quality of synthesized speech on a scale of 1 to 5. 1 is bad and 5 is excellent. And this slide shows the MOS result or ground truth mel-spectrogram inversion. As we can see, parallel WaveGAN and HiFi-GAN Vocoder can synthesize the speech comparable to the original speech. Remarkably, HiFi-GAN Vocoder got the 4.59 MOS score with the gap of 0.10 compared to the ground truth. And it means that the synthesized speech is indistinguishable from the original speech. And RTF valued 0.011 means that we can generate the synthesized speech with first inference speech. And for generalization to NC speaker, we use 10 utterance of 2 NC female speaker, and this table showed the MOS results of generalization. We can see that our model can generalize well to NC speaker. We got MOS score 4.42 and 4.48 for HiFi-GAN. And this is the MOS result of end-to-end Myanmar speech synthesis with independently trained neural vocoder. We got the MOS result of tacotron true and HiFi-GAN 4.37 MOS score and tacotron true plus parallel WaveGAN get 4.33 MOS score. We can clearly see that Myanmar end-to-end speech synthesis with independently trained neural vocoder can get the highest can get the good synthesized speech. And let me conclude my presentation. Both parallel WaveGAN and HiFi-GAN model achieve high fidelity speech synthesis with first inference speed, showing the ability of generalizing to NC speaker. GAN-based model, even trained on a small dataset with limited training step, can achieve high quality speech with low resource language. And our future work will focus on the mel-spectrogram generator to better capture the processing of speech. We will use GAN-based vocoder in various end-to-end speech synthesis settings. And these are the reference of my presentation, and thank you for your attention.